Petrović. I'm from the Department of Strength of Structures, Faculty of Mechanical Engineering, University of Belgrade. And I will show you structural analysis of bucket wheel excavators, load-bearing steel structure. This construction here is a bucket wheel excavator. And we will talk about this load-bearing structure most of the time. So when we talk about safety or reliability-based analysis, there were several studies in the past that were dealing the same problem, but they were dealing of safety in work, which included mechanical and system failures. And based on the history of those failures, reliability of the structures were assessed. But here we are dealing with pure structural reliability, which is based on stress distribution in this construction. In the first place, I will introduce you to this construction. This is bucket wheel excavator. It's the first machine in the chain of coal production. So it is very important for this construction not to fail, because there is a double cost: the cost of reparation and the cost of lesser production in the whole chain. So this machine is marked as really important structure, and we obtain this structure because it's complex, it's big, and it is important construction. So we are talking about structural reliability of these constructions. When you assess construction, you usually do some numerical calculations, you get stress concentrations, and you compare stress concentrations to the yield limit. And in that way, you didn't get into your analysis the overall structural response and all the uncertainties that could happen to that construction. You just compare one number to another and you finish your analysis there. But here we are dealing with structural reliability, and we are dealing with we include all the uncertainties and the overall response of the construction. So this is a good way to compare two constructions. When you use usual methods, you have one construction not failed and the other not failed if their maximum stress is smaller than the yield limit. But you don't know which one is better. And here we use this method to compare, to compare two structures, to describe them with just one number, and to say this one is better than the another. So firstly, numerical analysis was done. This is computational model. You can see here undercarriage, axial bearing between the undercarriage and slewing platform, and you can see here the pylons. And here you would have a bucket wheel boom and counterweight boom on the other end of the construction. But this could be load-bearing structure here. Results are obtained using software comics, which is finite element method based software. And it's suitable for me because you have full control over the mesh and over the equations implemented in that software. So I use it instead of some commercial software. And here you can see stresses in kilonewtons per square centimeter. And you can see here zones of stress concentration as well. So this model is mapped in a way to catch all spots, the overall response of the construction. That means that we included values in here and in here as in place in stress concentration, but in some other elements that in this load type doesn't have a high stress level, but in some other would have a large stress level, we also included these parts because they also join the overall response of this construction. They represent overall response of this construction. So we had 50 functional zones, and in them we got stress values. Here you can see all the zones. This is, for instance, undercarriage. This is slewing platform, and those are pylons. And both undercarriage and slewing platform consist of two horizontal plates connected with vertical plates and with cylinders. So we got, I don't know, for instance, I think 5 spots in every plate that included zones of stress concentrations, zone of the back supports, and someone here in the zone without a high stress level. And that was the philosophy of mapping the model. So pylons were divided into zones, into 6 zones. In each zone we got two spots, right pylon, left pylon, and some zones of stress concentrations in these truss that connects the pylons. We also got stresses. So then we got into probabilistic analysis. Here you can see histogram of the stress on horizontal axis. You can see stresses, and on vertical axis is frequency of those stresses. As you can see, the most of the elements, the most spots, has a stress between 45 and 65 megapascals. And here you will see a long tail. This includes zones of stress concentrations. So this histogram is non-symmetric. So we formed probability density function, and it's log normal because of this shape of the histogram. And then we transformed it to a normal function, and then we will compare that function to capacity of the construction. Here it will be clear for you what is capacity and what is demand. This represents stress distribution in the whole structure. This represents yield criterion formed in this way because we will usually compare this stress value with this value and say our construction is not failed. But now we get some uncertainties in the material itself because not only steel S355 does have yield limit this, they are much stronger and much weaker steels. So that distribution was got in here, and this is our stress distribution. So this is our demand and this is our criterion. Because our demand is lower than our criterion, our construction considered to be not failed. But now, since we are all structure engineers, we introduce some safety or some reduction factors in a way to gain our construction to be more safe. So when we introduce reduction factor of 0.67, we have this curve. And this shaded area here, that's our probability of failure. And we define our reliability as 1 minus probability of failure. And we used Monte Carlo simulations to conclude, to get our probability of failure. Monte Carlo is one simple tool. We used 10,000 different values. You practically, I can explain it simple. You bomb this surface with 10,000 spots, and then you bomb this surface with 10,000 spots, and overlapping gives your probability of failure. So this shaded area is our probability of failure. When you reduce reduction factor to gain more safety, then you will have a larger probability of failure, and you will have a smaller reliability, and beta would be reliability index that serves you to describe your construction with only one number. As you can see here, when RF is 1, that means this curve, your probability of failure would be negligible, and your beta would be 4.26, and your reliability would be high, would be almost 1. But when you have 0.67, your probability of failure would increase. I don't know, when you get there, it would increase, and that one would decrease, and beta would get smaller. So, once again, I was talking about pure structural reliability of this construction based on stress distribution, and we are planning to introduce even more loading cases in this analysis. I missed to tell you in the beginning that this stress was obtained for loading case that included that weight of this construction, that weight of all of these parts, and also included workload. Workload means overall digging force, including vertical, lateral, and that one digging force as well. And now we will include some more, and 60% of work life, this construction is loaded in that way. But the other 20%, it is loaded just by that weight, and the other 20%, it is loaded by inertial forces that can be dangerous. You see here 2 large masses, and when rotary movement is braking, you have inertial forces caused by these 2 large masses, and that could be dangerous for the structure as well. So we will introduce 2 more loading cases, and we will introduce buckling criterion. Here under pylons, you have vertical plates that are compressed, and they are already stress concentrations. But your criterion for buckling would be even harder than your criterion for yield limit, so your probability of failure would be even larger than in this study. And our plan is to introduce those 2 and get some more informations. And this is just a resume of everything that I previously said. And in the end, I would like to thank you for your attention. And if you have some more questions, you can contact me using my email address.
Okay, thank you for your very nice, interesting case study.
Thank you.
We are now open for discussion. We have time for a couple of questions. Please, Greg.
Please, could you go to the slide when you showed the distribution of the stresses?
Okay.
Because I'm not sure I got your point. With the histogram, later on there is a slide.
Okay.
Yeah,
here?
that one.
Okay.
I'm not sure I got your point in the sense that the fitted distribution, that one, okay, is the variability of the stress across the structure, or
yes, across the structure. We assumed that those values are independent one to another, and we created histogram just using stress of this construction.
Yeah,
I understand your question, because some papers dealing with this are dealing with stresses in one load case, the other load case, and the other load case.
No, the question is,
okay.
where is the variability of the external load? Because in my experience, I would use such kind of probability distribution to get the variability of the external load in one point.
Yes, of course. You're completely right. Those are those 3 cases that we will introduce to this study later. We will introduce different loads and compare them. You connect them in line, and then you get the whole picture. So,
if I may add, I'm sorry. No.
Maybe another colleague. Please.
Okay, thank you very much for the presentation. About the properties of the material, did they include the corrosion environment in the properties of the material?
No, we haven't. That's the idea to do later.
Ah, okay.
to introduce some more factors that could affect the whole structure and the whole analysis. All the other uncertainties that could affect this construction. But this is just pure structural analysis for now. So, thank you.
Yes, please.
I was a little confused to see you applying reserve factors to your allowable stress, and wondering when you captured uncertainty about the stress distribution
Yes.
for a given load, when you've captured uncertainty about material.
Yes, this is the
variability.
uncertainty of the
Yeah.
stress and of the material. Yes.
Yeah. So what's your reserve factor? What's your varying reserve factor to capture?
Factors are introduced to get more safety. All the structural engineers introduce some reserve factors to make their construction more safe.
Okay. But that's normal. That's normal when you're using a single value of yield.
Yes, of
predicated
course.
on a
Yes,
particular reliability.
yes.
Yeah.
Yes, that's the way for you to achieve your construction not to fail when you're using traditional way of.
Not to fail. To
Yes,
a certain.
yes.
To a certain implied level of reliability.
Yes.
Which we don't know.
Yes, of course, I agree.
Okay, thank you. Maybe a last comment on my side as well. Just complementing what was already said, maybe regarding the numerical model, I would also make some comments because we have also uncertainty from modeling as well.
Yes, of
And,
course.
this structure already exists?
Yes.
So maybe are you thinking to put some strain gauges just to have
Yes,
kind of validation?
yes, of course. Yes, to get the correlation of the numerics and the real structure.
Because
Yes.
dynamic effects, you should also.
Yes, of course. Accelerations
Yeah.
should be measured also.
Okay, thank you very much for your very interesting presentation.
Thank you.